Okay, to finish up our topics from Chapter 6, we're really just going to build on to the stoichiometry ideas that we've covered so far with mole and mass relationships in a balanced equation. So the types of problems that we've already looked at look like this. 1 mole of nitrogen. We'll take the time to write this out just to review what we've already done. Reacts with 3 moles of hydrogen to produce 2 moles of ammonia. So regardless of what the question is, we should be able to write that series of mole equalities. We also could write the individual, and I'll try to squeeze these in. 1 mole of nitrogen is 28 grams of nitrogen. 1 mole of hydrogen is 2 grams. And so here we're just relating each substance to its molar mass. So this is a series of equalities that we discussed would maybe be a good idea at first to write down so that we can look at a problem like this. What is the mass of ammonia? So we're looking at ammonia and we're comparing it to an amount of hydrogen. How much ammonia can we produce from 40 grams of hydrogen? So I'll just go through the setup with this problem. This should be a review of the stoichiometry problem. First, we have to convert grams of hydrogen to moles. And that equality is this one here we've written down. 1 to 2. And the reason we do that is so that we can convert moles of one substance to moles of another. In this case, moles of hydrogen are related to moles of ammonia. And then lastly, we go ahead and convert those moles of ammonia to grams. And the relationship's right up here, 17 to 1. All right, so this is pretty straightforward calculation. We can put this in our calculator. I think we'll get 227 grams of ammonia. I'm trying to do this from memory, so it's possible that I'll make an error here. 227 grams of ammonia. Now that's what we get from our stoichiometry calculation. This, by the way, is a maximum. This is the most ammonia we could expect to make. It's also a theoretical amount. In theory, this is the amount of ammonia we could expect. But probably we're not going to get that much ammonia. Just like when you're doing a recipe, you're making cookies, the recipe says you should yield 3 dozen, and you don't always get 36 cookies. The same thing happens in a chemical equation. So 227 is the most ammonia we could expect to make. The problem might then go on to read something like this. All right, so what if only 189 grams of ammonia is actually produced? What is the percent yield? All right, so this is a way we like to express what goes on during a chemical reaction. Sometimes we don't get as much as we expected. So we like to express how effective a chemical reaction is by finding something called percent yield. And it's always found this way. The actual yield divided by the theoretical yield. So it's really a part, the part that you actually make, over the whole. What did you expect to make? Times 100. So where is this information likely to come from? The actual yield can only come from experiment. So this value for you is probably going to be given. The theoretical value, on the other hand, you can always find using a stoichiometric calculation. So this is the basic formula for percent yield. Let's do that for our ammonia reaction. So we're going to calculate the percent yield actual over theoretical. And what is our actual value? This reaction actually produced 189 grams of ammonia, even though we were expecting maybe 227 grams. This one we figured out from our stoichiometry problem. This one was given. And then we divide, grams cancels, and I think you'll get about 83%, which for percent yield for a chemical reaction is actually pretty high. That's a pretty decent percent yield. All right, so let's look at a homework problem. All right, so this is problem straight from your homework, problem 60. Your numbers might be a little different. We have a balanced reaction. The question is, what is the percent yield for the reaction if you react 65 grams of iron oxide and it produces 14.7 grams of iron? So first of all, notice that this problem is a little bit different because it's the first time we've had two pieces of mass data given in the problem. So then we got to decide, do we start with the 65 grams or do we start with the 14.7? So let me reread this to you, and I'm going to insert a word that will help you decide. What is the percent yield for the reaction if 65 grams iron oxide actually produces 14.7 grams of iron? This is the actual. So we're not going to do anything with it right now. I'm going to write it over here. 14.7 grams of iron are actually produced. So that means I need to know how much iron could have been produced. I need to do a stoichiometry calculation and figure out the amount of iron. But I'm going to start with the given problem, the given information in the problem, which is 65 grams of iron oxide react, and I need to figure out how much iron, in theory, could we have made. All right, so again, you could take the time to write out all of your mole relationships. You could take the time to write out all the molar mass relationships. I'm not going to take the time to do that here. I'm just going to pull them out from the balanced equation. I know the first thing I have to do is convert moles of iron oxide to grams. So the molar mass is 160. Then I can convert moles of iron oxide to, what am I trying to find? I'm trying to find moles of iron. So I go up to the balanced equation and see that the ratio is 2 to 1. And then in my last step, I just need to convert moles of iron to grams of iron. 1 mole of iron is 56 grams, I think. Okay, so what is this going to tell me? When I calculate this dimensional analysis, 65 times 2 times 56 divided by 160, this is going to tell me, in theory, how much iron I could possibly make. This is the most iron I can expect to make if I'm reacting 65 grams of iron oxide. So that 45.5, I'm going to take up here and plug it into my theoretical and compare it to the 14.7 that was actually produced. Times 100, that will give me my percent yield. And as I recall, it's going to be about 32%. So it's kind of a low percent yield, actually.